Alright guys, so for this unit we're going to be dealing with 2D motion, and in order to analyze two-dimensional motion we need to understand how to use vectors. And so the whole idea here is that we're going to have some sort of resultant vector, say that looks like that. And when we have a resultant vector we can always split it into an x component, and we can split it into a y component, and we can have an angle theta. And so when we're dealing with vectors, it's important that we understand our trig functions from SOHCAHTOA, and that we also understand the Pythagorean theorem. So when we're looking at these couple of example problems, we'll be using our three trig functions, sine, cosine, and tangent. We'll also be using the Pythagorean theorem, and we'll be dealing with resultant vectors, x components of vectors, and y components of vectors. So let's look at our first example. Alright, so for our first example, let's say that you walk 121 meters to the south, and then you turn and walk 42 meters to the west, and we want to know what is your resultant displacement. So the first thing you're going to want to do is just kind of sketch out this motion. So you start somewhere and walk to the south, and we walked 121 meters. So we show an arrow pointing down, and we label it as 121 meters. And then from the head of that arrow, we do our second arrow, which is 42 meters to the west, which would be to the left on a map. So there's your 42 meters to the west. And so here is your delta y, and here is your delta x, and we want to find a resultant displacement. And we'll call the magnitude of that delta r. But remember that displacement also has a direction, and so we're going to label this angle where we started theta. And so that theta is going to give us the direction of our displacement. So first of all, to find the magnitude of our displacement, we're going to use Pythagorean's theorem. So delta r has to equal the square root of our delta y squared plus our delta x squared. And so if we solve that, we will get 128 meters. So what that tells me is that I finished 128 meters from where I started. So that is the magnitude of my displacement. But then I also need to be able to describe that direction. So what I'm going to do is calculate that theta from where I started there. And so theta has to equal the inverse tangent of opposite over adjacent. So in this case that would be 42 divided by 121. And if I take the inverse tangent of 42 over 121, that comes out to 19 degrees. Now, just 19 degrees is not really enough to tell someone a direction. So, if I go back to my sketch there, I see that first I went to the south. So this first line I drew here was going to the south. And then this angle tells me how far to go towards the west from south. So we would describe that angle as 19 degrees west of south. Now, it would have been possible for us to sketch our triangle the other way. We could have gone to the west first, and then we would have gone to the south. And if we had done that, our delta r would still come out to be 128 meters. But now if we calculated this angle theta, it would come out to 71 degrees. But this time we went to the west first, and then this angle tells me how far to go towards the south from there. So that angle would actually then be south of west. So 19 degrees west of south and 71 degrees south of west are actually the exact same direction. One tells me face south and then turn 19 degrees towards the west. The other one tells me face west and then turn 71 degrees towards the south. And in both of those cases we'd end up facing exactly the same direction. Alright, let's look at another example. So for our next example, we're given the resultant and looking for x and y components, which is the opposite of the last problem. So let's say that we have a boat traveling at 15 meters per second at a direction that is 62 degrees north of east. So the first thing I'm going to do is draw my vector up and to the right of 15 meters per second. And then my angle is 62 degrees north of east. So to sketch out my triangle, I'm actually going to go east first and then north. So I go to the east, and that will be my x component of my velocity. And then I'm going to go north, and that will be the y component of the velocity. And by going east first and then north, when I draw my theta at the beginning, that theta will be north of east, because if I'm facing to the east, then this angle now tells me how far towards the north of there to go. So here we're just going to use our trig functions. So that theta, of course, was 62 degrees. And of course the sine of theta has to equal the opposite divided by the hypotenuse. So if I rearrange that, then I can say that Vy has to equal 15 times the sine of 62, and that comes out to be 13.2 meters per second. And same thing for the x component. I would have to use cosine in that case, equals the adjacent over the hypotenuse. So rearranged, I can say that Vx has to equal 15 times the cosine of 62, and if I solve for that, I get 7 meters per second. So what that tells me is that if I'm going 15 meters per second, 62 degrees north of east, then I'm actually traveling 13.2 meters per second to the north and 7.0 meters per second to the east, and doing both of those things at the same time. Alright, so for our next problem, we're going to kind of put both of these things together. We're going to look at what happens if we have two different vectors that we need to add together, and both of those vectors are at angles. Alright, so for this problem, an airplane is set to fly 68 meters per second, 23 degrees north of east, but the wind is blowing 24 meters per second, 18 degrees south of west. So what is the velocity of the plane? So what happens here is we set our plane to do something like this. But then we have wind blowing something like this. And so our resultant velocity is going to end up actually looking about like that. And I should have put my 68 over on the other side so it wasn't in the way there. But what's happening there is that wind's kind of blowing in our face and to the left, so it's kind of blow us a little off course and slow us down at the same time. So in order to do this problem, the first thing we have to do is find the x and y components of both the plane setting and the wind. Okay, so I've sketched out triangles for both the airplane setting and the wind, and then the next thing I'm going to do is use both the sine and cosine functions in order to find the x and y components of both the airplane setting and the wind. So for the plane, we figure out that the x component of its setting is 62.5 meters per second to the east, and the y component of its setting is 26.7 meters per second to the north. Okay, and now I've found the x component of the wind, which comes out to 22.8 meters per second, and I've made it negative because it's west or to the left, and then the y component of the wind comes out to 7.4 meters per second, and I've made it negative because it's to the south or towards the bottom of the page. So we followed our normal sign conventions there. Alright, now to find the resultant x component, we have to take the x component of our plane and add it to the x component of our wind. So we take our 62.5 plus negative 22.8, and we get 39.7 meters per second. So 39.7 meters per second to the east. And to find the y component of the resultant velocity, we add together the y component of our plane and the y component of our wind, and when we add those two things together, we get 19.3 meters per second, or 19.3 meters per second to the north. So the final step is to sketch out our resultant, so we need to go 39.7 meters per second to the east, And we need to go 19.3 meters per second to the north. And then here is our resultant velocity, and there's our angle theta. To find a resultant velocity, we'll use the Pythagorean theorem. And then to find theta, we'll use the inverse tangent of opposite over adjacent. And so when we solve for both of those things, we get 44.2 meters per second at an angle of 26 degrees. And that angle would be described as north of east, because we went east first, and then our angle tells us how far we go to the north of that. Alright guys, so good luck with those problems I asked you to try over this weekend. The problems also ask you to do some things graphically, which is where you actually use a ruler and protractor to get these same angles by making a scale drawing. You can go ahead and give it a try if you want to, and we'll talk about how to do that in class tomorrow. See you then.